Okay, so again, degree centrality is just the number of neighbors of a vertex. So for vertex 0, it has 3 neighbors, so its degree centrality is said to be 3. Vertex 1, it has 2 neighbors, so its degree centrality is said to be 2, and so on. Now, one thing we want to do with any centrality metric is, after we compute it, we want to rank the vertices in the decreasing order of the centrality values, so that we can pick up the vertex that we want to process further for some application. So in this case, if you rank the vertices based on the degree centrality, you will observe these ones in yellow, 0, 2, 3 and 5, to have a larger degree centrality. So each of them had a degree 3. 0 has degree 3, 2 has degree 3, 3 has 3, 5 has 3. So one weakness with the approach is, when you want to rank, you want to kind of have unambiguous ranking, in the sense that you would prefer no two vertex to have the same value for centrality metric. If two vertices have the same values for centrality metric, then there's a tie like this: 0, 2, 3 and 5. Okay, so that's a weakness of degree centrality approach, because underlying reason is it's an integer, and it cannot take up more values or more unique values. So that's one reason why degree centrality is not preferred to rank the vertices based on degree. Even though it says degree centrality captures the number of neighbors, the degree of a vertex, it's not used to rank the vertices based on degree. So what is preferred is eigenvector centrality. Okay, so let's see now this in detail. Now, by the way, so how to compute the degree centrality of a vertex? So this is just we don't want to do this for degree centrality, we want to do this for eigenvector centrality. But so since we are going to see this in eigenvector centrality, I just added this slide here to as a way to compute the degree centrality. You can use adjacency list approach and discount the number of neighbors. That will be more efficient than using this matrix approach in reality, in real world. So what we do is, we have the adjacency matrix of the graph, and you all know how to get the adjacency matrix. So you have 1 if there's an edge between two vertices. If there's no edge, the entry is a 0. So 0 has an edge to 1, 2 and 3, and no edge to 4, 5 and 6 and 7. So that's its entry for the adjacency matrix. Now for 1, you have an edge to 0 and edge to 2 and nothing else. So that's 2 ones. For 2, it has an edge to 1, 0 and 3, 0, 1 and 3. Now one thing you have to realize is, this is a symmetric matrix, and the contents of the upper diagonal are a mirror image of the contents of the lower diagonal. So it means if I have 0, 1, 1, 1 followed by these 4 zeros, we can write it as column 2, 0, 1, 1, 1 followed by these 4 zeros. And 1, 0, 1, 0, 1, 0 followed by 4 zeros. You can write it column wise like this. So once you get the adjacency matrix, what you do is you multiply that with a unit vector of all ones. And we saw matrix multiplication, how to do it before. So this is 8 by 8 matrix, and this is an 8 by 1 matrix. This is actually a vector. So if you have an 8 by 8 matrix with 8 by 1, the resulting product is also going to be 8 by 1. Okay, so the rule for matrix multiplication is this. So 8 by 8 multiplied by 8 by 1, 8 rows and 1 column, the product is going to be 8 rows and 1 column matrix. Okay, so how to do the product? So we want to get the entry corresponding to row 0, column 0. There's only one column here. So row 0 multiply with column 0. which is this row multiplied by this entire column. So 0 times this 1 plus 1 times 1 plus 1 times this 1 plus 1 times this 1 plus the 4 zeros multiplied with these 4 ones. And what you get as a product is actually the degree centrality of these vertices. So these are the vertex IDs corresponding to that entry. So we can, that's how find out the degree centrality of the vertices. It has lots of applications. Now you notice that these 4 vertices 0, 2, 3, 5 have the largest degree centrality. So how to break the tie, and a solution is to use eigenvector centrality for this. So eigenvector centrality, as I said, is a measure of the degree of the vertex as well as the degree of its neighbors. Okay. So we'll go through some sequence of iterations to determine the eigenvector centrality values for the vertices. So this method is called the power iteration method. So the first step is similar to how we find the first iteration is similar to how to find the degree of the vertex. So what we'll do is we'll compute the degree value. So we have the adjacency matrix multiplied by the unit vector of all ones. So we get the product vector. So now we normalize the product vector. So how we normalize the product vector? Find the sum of the squares of the entries, the normalized product vector. So that means 3 square plus 2 square plus 3 square plus 3 square plus 2 square plus 3 square plus 2 square plus 2 square. So now once you get the sum of the squared values, take the square root of that sum of the square values. So that's what I have written here as the normalized value 7.21. So that's the square root of the sum of the squares of these values. And then what you do is divide each entry here by the normalized value 7.21. So 3 divided by 7.21 is 0.416. 2 divided by 7.21 is 0.277, and so on. So that's the end of the first iteration. So what we'll do is repeat this process for subsequent iterations. The only difference is, instead of the unit vector of all ones, you will use the final normalized row vector. So now what you do is normalized column vector. So now in the second iteration we will use that column vector as the argument here, and then multiply with this adjacency matrix. So again, same multiplication approach. So this row multiplied with this column will get 1.109. This row here multiplied by this column here will get 0.832. The third row here multiplied by this entire column, we get 1.109. So then once you get this product vector, again normalize it. So for that we need to find the normalized value. So it is 1.09 square plus 0.832 square plus 1.109 square. Plus 1.109 square, 0.832 square, and so on. Then take a square root of the sum of the squares, you get 2.59. So now divide each of these entries 1.109 and all these things by 2.59, we get 0.428, 0.321, and so on. Now we'll continue the iterations like this. So the next iteration we'll use this column vector as the argument and do the multiplication. So same rule for multiplication is applicable. So this row, first row multiplied by the first column will get 1.177. Then second row multiplied by the second column will get 0.856, and so on. So then again find the square root of the sum of the squares of these normalized values, you get 2.567, and then divide each of these entries 1.177 by 2.67, you get 0.441 and so on. You can go for one iteration. You see the values of the normalized value, it is 7.21 and then 2.59 is 2.67. It has to converge at least to one decimal for us to stop. So the next iteration, we will multiply the graph with the normalized column vector that we got at the end of the previous iteration as entry here. So we'll do the multiplication and find the normalized value, which is the square root of the sum of the squares of the entries here. And then once you get the normalized value, divide each entry by that normalized value. So 1.243 divided by 2.64 is 0.471, 0.922 divided by 2.64 is 0.349 and so on. Now you could see the entries in the column vector kind of start converging, they kind of getting closer. So that's actually the criteria we should use to stop the iterations. Okay, how close are the entries in the column vector that we get? But that will take a lot of iterations. So for the simple graph of 8 vertices, it took 7 iterations. Okay, so as a convention, we'll stop if the normalized value has converged to the first decimal. So we have 2.67 and 2.64 here, so that 0.6 is the first decimal level of precision. So we'll stop if we encounter something like that. So these are the values of the eigenvector centrality values of the vertices after 7 iterations, and this could be obtained using the Java program I gave you on this graph. Okay, and these are the corresponding eigenvectors. Also the principal eigenvectors or the eigenvector centrality. So what we end up with finally is the principal eigenvector, and the entries in the principal eigenvector correspond to the eigenvector centralities of those vertices. Okay, so any question on this? So I have few more examples. So what I encourage is practice it. We'll take a short break. So practice these examples if you have time. So we'll meet at 7:30. So try out these examples I have here using the jar program I gave you, and see if you can get at least one iteration done or one example done. And we'll come back and look at those examples and move on. Okay, so let me save this video.